might have close relationships with.
Okay, so I'm gonna show you how to use StarV to verify, quantitatively verify a neural network. Okay, I have StarV installed in my computer right now. So now I'm gonna walk through the process. Here you have 6 steps. We're gonna do one by one. So first, we need to activate the StarV environment. So we do conda activate StarV. So here you can see that StarV have multiple folder, but everything we are talking here is in tutorial. So you can see that in this tutorial, they have many subfolder. Okay, so for quantitative verifications, you just go to see. So here you can see tutorial for CNN, tutorial for FFN, tutorial for GRU, and everything is there. So you can open, for example, tutorial for feedforward neural network. I use Emacs to open it if you are familiar with Emacs. So here is the tutorial how to verify our neural network. Okay. So in this tutorial, they give you how to do qualitative verification, how to do quantitative verifications. So you look at what we import here. You can see that we have, for qualitative verifications, we have some reachability methods here. Reach exact breadth-first search, reach approach breadth-first search, okay? And then for quantitative, you also have qualitative verify exact breadth-first search, qualitative verify approach breadth-first search, something like that. That I open it here. So these are the methods that implemented in the verifier modules that give you all the methods you need to verify your neural network or your neural network control system. And then if you want to plot everything, then it's gonna be in the util model and in the plot module, okay? So you can see it here. Yeah. So you can plot a star set, you can plot a prop star, or you can plot prop star signal even, yeah. So yeah, you can check that util model, okay? So this tutorial gives you how you can construct a neural network object manually. You can do it. How you can construct a neural network objects from math file. If you train a network in MATLAB, you can actually do it like this, right? So they give you, and then how you can evaluate the network with a particular input vector. You can also do it using the evaluate methods. When you construct the neural network object, you can use evaluate methods here to compute the output for particular input vector. And then you have qualitative reachability here. So now I'm gonna focus on quantitative, okay, the thing we discussed. Okay, so here. So you look at the function here. So here we're gonna do a quantitative verifications for a tiny network. So the first step is construct feedforward neural network. Here we construct manually, okay, the object, and then you construct the input set, okay, and then you specify the property, and then you specify the number of cores you want to use for verification, okay, and then you use the quantify verify breakfast search, quanti verify breakfast search method to verify the network. So the network is going to return to you actually 7 results. The first one is the reachable set when you compute the reachable set. The second one is going to be the unsafe set. The third one is going to be the counter example in book set. And then the lower bound and upper bound of the satisfaction probability. And then the mean and the max of the bound of satisfaction probability. Yeah. So here we bring and plot all the things here. So you do the same thing if you want to do over approximate verification. The only thing you need to change here is the filtering. Okay. When you don't do any kind of filtering, then you are doing exact analysis or exact verification. When you filter, you're filtering, that means you're gonna ignore the branch with a lower probability here. For example, any branches that have the probability smaller than 0.1, just ignore that. And then you do the same, right? So it's gonna give you the approximate result, okay? So that's how it's work. Okay. So now let I run the script. So the first one, I'm sorry. This is the inbox set is produced. Sorry, it takes some time. Now let I turn off this. So it's gonna produce the exact set for you, okay? So this is the exact reachable set with the probability for each partition. So here you can see that the exact set contain multiple subset here with probability. And this is the unsafe set. So you think that all the sets here have y1 smaller or equal to -2, right? You have the unsafe property is smaller than -2. So here it's gonna cut the reachable set, locate where it is unsafe, and then return the set for you. So you can plot that. And here is gonna give you, okay, the counter in book set. So what area of the inbox set lead to the unsafe state? So it's gonna plot everything with the probability. Okay. So the same things for approximate methods. It's gonna give you approximate reachable set, and then here you can see approximate unsafe set, and then approximate counter in book set. See, yeah. So you can see what is produced here. So you can see it count the number of prop star, right? And then if you use filtering, then it's gonna filter out some prop star that have probability smaller than 0.1. So it's gonna give you like the number of ignored prop star in reachability is 3, right? The number of remaining prop star is 3, something like that. And let's do it layer by layer. So we have two layer here, right? I think one ReLU layer, sorry. So that means layer 1 is ReLU, layer 2 is gonna be Diabo. Yeah. So that's how we do quantitative verification. But the most critical result we want to get is what is the lower bound and upper bound of satisfaction probability, right? So that's exactly where you get here in the code. So you can see that now I don't care about the reachable set. I care the other for our book here, okay? The lower bound of the satisfaction probability, the upper bound, the mean and the max, okay? And then I just bring all of them. You can see that. So here, yeah, you can see here the lower bound of satisfaction probability, the upper bound, okay? And then the mean and the max. So the mean and the max here consider the tail of the distribution. Is there any questions when I move to another demo sections? Okay, so that's the first demo sections about quantitative verifications of neural network, which is an open loop verification problem. So now we're gonna go to another interesting topic. So how you gonna verify, quantitatively verify temporal properties of a neural network control system? That means you have a neural network controller control physical plant dynamics, right? So the key idea here is that you're gonna use not like only probabilities reachability, but you use depth first search. I'm gonna tell you why we need depth first search. So actually, to define the temporal property of the system, we use the logic, the set-based logic called ProfStar temporal logic, as Paul mentioned in the morning. Previously. So this set-based temporal logic consider and define the semantics on a single reachable set traces. So using depth first search, you're gonna construct all the traces, okay? And it's a reachable set. It's not real-time signal like signal temporal logic, if you know about that. So it's very different. So I'm gonna explain a little bit about the approach here before we do some hands-on activity. So you have, we consider a system, a simple system. You have neural network controller control linear model, okay? So for ProfStar reachability, you actually can construct probability reachable set traits for the system. And then from that, for specification, you have specification phi. And then for verification problem, you want to check whether or not the reachable set satisfy the specification phi, okay? So it's going to return you sat or unsat. But here we want to do something more than that. We want to compute the probability of our satisfied phi, okay? So let me give you an example. So for the ACC, which is adaptive cruise control system, using neural network like this, you have a safety properties. It's something like the distance between two cars is always larger or equal to a DC distance defined by the user. That's called safety specification. So you can see that at any time, you want to check whether or not D is larger than the D safe. That's it. But for temporal specification, it gives you more expressive or more complicated requirement for the system. For example, here you have something called like eventually between 0 and t if the distance between two cars smaller than this safe, then there's always the case that this remain in the next 5 seconds. So that means we want to check, oh, if it's unsafe, then the unsafe state remain for the next 5 time step. So this is called temporal behavior that we want to verify. So you can see that is more complicated than the safety specification here, okay? So this is how we interpret that complicated specification. So if two car is unsafe condition, then the unsafe conditions are maintained in the next 5 time step. So now let I talk with you like how we can actually compute the reachable set, all the reachable set trace of the system and use that to compute the probability of satisfaction here. Okay, so here you have the system. Okay, so I'm gonna walk through the depth first search idea. It's implemented in StarV, and we already optimized that to make it efficient. So here you can see that we have 2 things to handle. You have the in-book state X. Oh, sorry, the plan state X. It's gonna feed back to the controller F, and then from the F we're gonna compute U, and then we feed back to the plan, right? So here, when you have S step t equal to 0, you have initial state x0, and corresponding to that, you have the outbook initial state y0, and then you map this y0 equal to cx0, and then you use that to compute the next control input. Okay, so it's gonna be u0 equal to f of y0, and you know that f here is neural network. So from a single set, it's gonna split into like multiple subset. That's the reason when you do exact analysis here, it's gonna return you after step 1 like mth sub control in book set. Okay, and now if I take the first one, I do the same, right? I take the first one. I'm sorry. From the control input set, you're gonna combine. You do Minkowski sum of the control input set with the A's x0. You just follow the dynamic here, okay? Because we have m control input set, then you have m new state. Okay, that's the first reachable set for the first step. And now if you, again, you pick the first one, okay? The first one in the reachable set, let's say at step 1. And you do the same, you're gonna generate another M2 control input set. And then you go that, and then you're gonna see that the number of reachable sets gonna increase, right? But when you do depth first, what is the depth first mean here? That means you know that x11 is from x0, and then x21 is from x11. So that means you construct a trace of reachable sets where you know that x0 produce x11 produce x21, blah blah, right? So the system the trajectory of the reachable set of the system is very complicated. But when you do depth first search, you can construct all of the reachable set trace where you know exactly the dependency between them. Okay, and using that reachable set trace, you can actually verify temporal behavior of the system. Okay, so that's one trace, and for the system, we can have like thousands of traces like this. Okay, so now we're gonna talk about set-based logic, which is the key for this thing to work. So we propose prop star temporal logic. It's fundamentally different from well-known logics using in control, like signal temporal logic, for example, very well known. The main reason is that this logic is defined on reachable set trace. It's not defined on real-time signal. So real value signal. So that's the key difference. So because of that, the quantitative semantics for this specification language is defined differently. So we build on concept called reachable set signal. Let I give you a very small example how the reachable set signal look like. So you have a very small example like this, okay? Then you have x0, and then you can compute x1, x2, x3, and x4. So you have 4-step probe star signal like that, okay? And x0 is defined like this. And follow the dynamic, you can compute x1, x2, x3, and x4. So you can see that the signal here is the set, okay? The set trait is not the real value signal. So now we want to define a syntax for this specification language. The syntax is very similar to what we have for STL. It's nothing different. So you can define using until operation or always operation, something like that. So it's similar. And here, the things we care is that we have bounded time interval. So that means this approach only works for bounded time verifications problem. Yeah. So now we have Boolean semantics. That means Boolean semantics give you sat or unsat. Okay, that's a binary result. So how we can get Boolean semantics? Actually, Boolean semantics defined on probe star signal is going to give you what? It's going to give you all of the constraint so that the trajectory of X satisfy Phi's content in this constraint, okay? So this can be defined recursively. So we can define recursive Boolean semantics for probe star temporal logic. So here I'm gonna give you intuitive example, how it look like and why it's different. So for Boolean semantics, there are one example, like if you have a reachable set RT at time t like this, and then you have the atomic predicate M, then RT satisfy mu here, it's gonna return you what? Return you a set, okay? So this contain multiple points that actually satisfy RT intersect with mu, okay? So now, this case, easy is convex, right? Now, if you have n, so you have two predicate, two constraint, phi1 and phi2. Now you want to check whether or not RT satisfy phi1 and phi2. So that means you need to know that RT need to satisfy phi2 and also satisfy phi1. So this is the intersection between these three sets, okay? And this case is also convex. But what about OR? So if you have phi1 or phi2, then you see that the satisfaction set now is non-convex, okay? So that's how the Boolean semantics can be intuitively represented in terms of set, okay? So you can see, if you know about signal temporal logic, you can see that the Boolean semantics defined is not about set, okay? It's just one constraint satisfaction, that's it. Okay, so now the thing that's more important is quantitative semantics, because it can give you, if a specification is satisfied, then we can actually compute what is the probability of satisfaction here, right? Using quantitative semantics. So you know that from the recursive definition of the Boolean semantics, you can come up with all the constraints for phi of R satisfied phi, okay? So this we can compute the probability of this constraint exactly or estimatedly. So for exact, you can actually convert this constraint into disjunctive normal form. So for disjunctive normal form, then the constraint is equivalent to a union of Brobst star, S1 to Sn, for example. So this we call disjunctive normal form, where Si is actually a Brobst star. And then we can compute the probability of this constraint, right? So R satisfy phi by just compute the probability of this union of Brobst star. And then we can compute it exactly using this formulation, okay? And so if we don't want to compute it exactly, because the number of Brobst star might be like 1,000 or even like it can go up to million, then we can estimate this satisfaction probability very quickly by just examining the probability for each Brobst star and take the max. So you're gonna see that if you take the max of P of X1 to Sn, then you say the max of that's gonna be the lower bound of satisfaction probability, right? So that's how we can estimate it. So now from the syntax, how we actually obtain the quantitative semantics, we can obtain the disjunctive normal form or disjunctive formula. So the derivation is actually kind of like a little bit tricky here, where you have two steps. First, you obtain the abstract disjunctive normal form, and then you realize the abstract disjunctive normal form. So for example, here, when you have the formula like this, then we leverage the SCOF, then we generate the abstract disjunctive normal form, right? Here, the number here, 1 to 2, is the time step, right? And then after this, we have abstract disjunctive normal form. We can combine with the reachable set for at each time step, then we gonna derive the constraint for satisfaction. So that's how we did it, okay? So here, for example, on our small example, you have phi 1, phi 3, and phi 4, something like that. So you have the Brobst star signal, right? And then you come up with, you want to compute the satisfaction of phi 4 on this reachable set signal. Then it's actually equivalent to 3, the union of 3 Brobst star, okay? So it's actually come up with some constraint like this. And then you can compute this satisfaction probability exactly, right? So that's the idea. Or you can estimate, right? So if you do exact, you can get the exact result. If you want to estimate, then you just estimate the max one. That's it. So that's the idea of quantitative verifications for temporal behavior. So now I'm gonna walk through the quantitative verifications algorithm. We have 3 steps. First, we want to construct all of the Brobst star signals using the depth first search reachability algorithm. And then for each Brobst star signal, we obtain the disjunctive normal form formula. And then from that, we compute or estimate the probability of satisfaction. So you can see here, the computational challenges here is gonna be the number of Brobst star signals grow exponentially in the Wood scale, right? And the length of the DNF also a big problem for computations because the number of Brobst star in DNF formulas can be very large. So we need to have efficient way to compute, right, or estimate the probability. So in this case, filtering become a very good use for reducing the computational burden for the methods. So you can see that we can filtering out the Brobst star signal with tiny probabilities. We can compute exact DNF probability if the length of the DNF is small enough, like 11 Brobst star. If it's larger than 11, we can estimate, okay? Something like that. Okay, so now we're gonna do some hands-on for this approach on StarV. So I'm gonna use ICC case study. I show you. So we have 5 steps here. First, we construct a neural networks control system object in StarV, and then we construct the prop star input set. Okay. The second step is the step we already did in the first demo. And now step 3, we specify the temporal properties. And then step 4, we verify under a network control system, again, that probability properties, sorry. And then we visualize the result. So the first one is constructing an NCS object in StarV. So we have 2 components. We have a neural network controller, and then we have plant dynamics. Okay, so we are working on graph-based modeling where you allow multiple components inside the system. So it's going to be much more complicated than this simple neural network control system architecture. So you have controller, you have plan, and then you also have reference inputs, and then you have output feedback channel here, right? So that's the simple architectures. So for verification example, we use learning-enabled ACC here. So you see that, yeah, there are 2 cars, and then they want to keep safe distance. And then if the car is in a safe distance, they want to reach the expected or desired velocity, speed, or something like that. That is adaptive cruise control system. And then we consider the initial condition here. So we have initial conditions for the lead car and then the ego car. So the dynamics of the system is represent like this, okay? So this is the physical dynamic. So the simulating architecture for the system, you can see we have a neural network controller which is here, and then we have ego car, and then we have the lead car, and then we have here is the reference sequence where you want to see like, okay, one is the time, the gap between when you apply the brake to stop the car to prevent to be safe, right? And then you also want to have the set point for the speed you want to your car to achieve. So that's the reference signal, right? And then here you have a single control input here. That's mean the acceleration values for the ego car. So the neural network try to output that for you. Okay. So that's the example. So now let us show you how we construct this neural network control system object in StarV first before we move to another slide.
And all that you show,
Uh-huh.
what is the answer depending on? Is that from initial conditions?
Yes, the initial condition.
So the initial conditions, because you had them.
Yes.
Normally distributed, or those are means, or what are those?
Yeah, so we're gonna talk about that. We actually do kind of man-made distribution for that, but in reality, that the mean and then the standard deviation is gonna come from maybe, sensor accuracy models. Yeah. So, but here I'm gonna show you how we can create props or input sets from these output, these ranges. So here we have, you can see that in this folder, we have tutorial for PropStar temporal logics for learning enabled system. You can open that. So there's a lot of things we need to import to make it work. So you can see that, let me show you, we have the neural network control system object here, okay? We have the neural network object, and then we have the dynamic object. It can be linear ODE or discrete linear ODE. Then we have bunch of set, and then we have the verifications methods, okay? Yeah. So let's see how we can construct the system. So you can see that we can load all the way and the bias of the controller. You construct the neural network controller here, okay? Using the neural network object, and then you load the plan dynamics. So you load the matrix A, B, C for the plan dynamics, and then you construct the plan model using the linear ODE object here, and then you discretize that by dt equal to 0.1, so to get the discrete plan model. And then you construct the system here, which is the neural network control system object with network controller, discrete plan model, and then you give the type of that. We call it discrete linear neural network control system. And then you can print the system information. So that's how it works. So let's try it here. So when you bring the system, it's gonna bring everything. So it's gonna bring the type of the system, the number of outputs of the system, the number of input, the number of feedback input, the number of reference inputs, and then it's gonna bring the neural network controller for you. It's gonna bring the plan dynamics for you, okay? So yeah, so that's the first step. We construct a neural network control system object, and that object contains reachability methods, verification methods that you can use for verifying the system. Sorry. So now let's move to the second step. So the second step, we construct the prop star input set. It's very similar to the section demo 211, right? But here we want to split the input domain into multiple subdomains so that we make the input set smaller, and then we can compute the reachable set faster. Yeah. Let me show you how we do it in the script. So it's come with the methods called initial state. So you can see here, we have the initial condition for the states of the lead car and then the ego car, right? It's gonna give you the bound for these states. And then from these bound, how can we actually come up with a nice prop star input set, right? So we just do cut up like man makes, like we use the coefficients parameters here, right? To adjust the distribution. So here we define the mean is gonna be the lower bound plus the upper bound divided by 2, right? That's the mean. And then we're gonna define the standard deviation here equal to this. And then when you adjust A, then you actually adjust the distribution. Like you adjust the probability for alpha to be inside the bound. Okay, so we want to adjust like 99% or like when you draw alpha, it's gonna go into the bound. So we usually adjust like that. But in reality, means or sigmas need to be given by maybe the sensor error model or something like that. Yeah. So here you split, right? You split the input set and then you construct the input set. Yeah. So when I run it, it shows you nothing. Sorry. So we split the set into our multiple subset, and then we book ID for each subset, and then you're gonna see that how we're gonna run a particular ID and verify that later. Okay. So now we're gonna go to step 3. How you specify temporal properties. So specifying temporal properties, you're gonna get some temporal and logic operator here. So for example, we define eventually something. We also define always operators inside StarV, so you can just load it and then now you make up your own specification, right? So here we want to have something like eventually the distance between two cars is smaller or equal to be safe. Okay. So yeah, so here, and then we also make another formula called always. We consider the relationship between the safety condition and then the velocity of the ego car. Okay, so let I show you in the code. So here you load all the operators and then you define the atomic predicates, and then you can use the formula object here, okay, to create the formula. So the first specification is going to be phi 1 is eventually between 0 and t. P1 is always satisfied. So what is P1? P1 is defined by this predicate. So let it run it. So you have this formula. You can print that. Okay. So that's the, I think, the third step, right? Fourth step. And now you want to verify the system. So when you verify the system, then there are a bunch of parameters you need to set. For example, you want to say, okay, what is the filtering probability, PF? So if you book it 0, that means they're going to do exact verifications for you. The number of steps here, which is T, right? What is the number of steps? The initial set. So the initial sets get from the initial set with some particular ID, and then the temporal span. Okay, so you have that in the verify parameters object, and then you call the methods called verify temporal specs. Okay, and then you're gonna get all the traces, the maximum satisfaction probability, minimum satisfaction probability, the reachable time, check-in time, verification time, something like that. Okay. So Let's look at here. So here you can see we use a function called verify temporal specs. You book the system and then the verification parameter. And that's it. It's going to return you all the things you need. And then you can actually visualize or plot the traces you want. For example, here is I just plot the first trace, okay, the trace 0, to see how the reachable set of the speed of the ego car compared to the distance between the car, the relative distance and then the descent. Okay, I just plotted. Here, I can run it. So it's trying to get all the traces, okay? So here is the one particular trace you want to plot, okay? So look at what it's doing right now. So first, we get all the traces using the depth first search, okay? So the total trace is 2. And then you verify the trace again, the temporal specifications. So to do that, you transform the SPAD to abstract disjunctive normal form, and then you calculate the length, right? And then you realize that abstract disjunctive normal form on the prop star signal, and then you compute the exact probability of satisfaction. Okay. So there are options we call show option. If you let show equal to 4, then these information is going to be disappeared. It's going to give you the result only. Okay. So I just wanted you to know like what exactly happened behind the scene. Okay. So here you can see that it's going to return you the maximum satisfaction probability. So here you have 2 specifications, right? So you can see that it's going to give you an array of satisfactions probability for each specification. So that means they only construct the traces one time, and then you can verify thousands of specifications using the same reachable set trace. So you don't need to recompute it, okay? And then it's going to return all the satisfaction probability for you. And here you can see the reachable time, the check-in time, and then the total verification time for each probability. So for each property, sorry. And then here is the reachable set trace you can plot, okay? So that's how it works. But let I mention one thing. So actually, if you want to you have full analysis about the verification result, then you should use the methods called verify temporal specifications for full analysis. It's going to give you actually 12 results. And then some results are very important because you give the estimation of satisfaction probability, how conservative it is. Okay, what is the conservativeness of that? Or it's going to return you the SAT traces. That means it's going to give you, okay, if it's give you SAT, then it's going to produce some particular SAT trace for you to visualize and check it by yourself. So you can get this SAT trace and visualize it and see whether or not it's actually true, right? So you can visualize everything. So you can use the plots, prop star signal methods here, okay, to visualize all the things you want. So yeah, that's gonna be all for the tutorial for today. If you have any questions, I'm happy to answer. And all tutorial script inside StarV I'm gonna show you quickly the user manual. Okay. Here, this user manual. So we have a very detailed how to use StarV. Okay. So you can take a look. Yeah. We have everything we present here, and then you can take a look and see how you can use StarV for maybe your project. Yeah. Yeah, that's gonna be all. Thank you. Yeah, you have all tutorial script in GitHub. So you can check it if you want. Any questions for me?
So I was just curious to know if in the, thanks, I think I'm loud enough. Okay. So thank you for the very nice tutorial. I was just curious to know, in the temporal case, given a dynamical system, if not necessarily one that is that has a control input, even if you consider an autonomous dynamical system without a control input, and if we are interested in verifying certain robustness properties, and you want to do it over a finite horizon, or you want to do it over in an asymptotic sense, is it possible to adapt the framework that you have developed?
So can you please just repeat only one time?
Sure. I'm curious to know that for a dynamical system where one has one wants to study one wants to verify if certain property holds in both space and time. Is it possible to extend your framework over a finite horizon where I can decide the horizon, and or I can study it in an asymptotic sense as well, where I can push the horizon as far as I want to? So what I'm trying to understand is, can this framework be extended, or there are limitations on the time frame over which the verification can be?
So yeah, does that mean you are asking about the scalability of the approach, like how the time horizons can be increased? That's correct?
So I think scalability can be studied in two ways. So one is the dimension of the system the underlying system, and another could be in time as well.
Yes, yes.
So because recently we have started studying some problems in opinion dynamics, where you have a multi-agent system and you want to verify if that kind of a system satisfies certain properties.
Yep.
So we are exploring some tools, and I was just curious if
we can actually extend that to multi-agents system.
And can you extend it in time as well? Meaning,
yes.
I think that you mentioned, like in one of the examples, that if I understood correctly, verification can be done up to t equal to 11 or something like that. But I was just curious if it can be done for longer intervals, and what does one have to pay for that?
So if you increase the time, then usually the commutation time is going to be increased.
Yes.
But it's actually not really the case. It's really depend on the specification. So actually, the length of the DNF deciding the time for computation. Okay. For some specification, magically the length of the DNF is very small, and then you can compute it very quickly. For some specifications, I can return you the DNF with a very long length, like maybe 1,000 approx star, and that's called the problem. So at that time, you need to know, like, whether or not in that case you need to use approximate methods instead of exact computation. So you can adapt it. But I can tell you that the approximate method still give you a very tight estimation bound for the satisfaction probability.
Okay, so maybe you mentioned it and I didn't pay attention, but I was just curious, are there any formal results on like saying that if you want to verify and you want to verify a certain property over a horizon T, that this is the computation time that's required, or this is the sample complexity, or something in that kind of space?
So I think like if you want to extend this to like multi-agent system, then the time complexity is gonna, I don't know, it's gonna increase. I believe it's gonna be linear with the number of the agents you handle.
Okay, thank you.
Yeah.
Thank you. Really quick question. Do you have a public development roadmap somewhere? You mentioned certain features you're currently in progress of developing. I'm wondering when can I expect such things? Thanks.
Yeah, it's gonna coming soon. So yeah, it's gonna coming in a couple months. Yeah, hopefully. Yeah.
Thank you.
So yeah, I share with you the main bottlenecks, right? The linear programming and memory. So if we target a real-world model, like a vision language model or yeah, like vision model with like attention mechanism, and how you handle that, okay? So LB doesn't work for sure. And if you cannot handle that, if you cannot handle the memory footprint, there's no way for you to can actually make these verification technologies work on the real world model. And we are pushing really hard for that. Yeah. Hopefully in the next 6 months, you're gonna see something far more stronger than this. Okay. And yeah, thanks. Any other questions? Okay, thank you so much. Yeah. I think we still have 30 minutes, so we can have coffee sooner.